Hello. Okay, let me share my screen real quick. We will go to this. Okay, and let me just start my LinkedIn stream here. Go live. Okay, that should be it. Okay, now I'm live on both. I'm live on both, so let's go. We're just gonna continue figuring out this open source model and gonna keep improving it. So I got my last live. In my last live, I finished muon optimizer. So casted linear, that's where we got to. So casted linear is same as linear layer, except I forgot. Let's see. So it builds on NN linear. It disables bias term, and it has FP8 support. And that's it. And we would use it on Hopper GPUs, so NVIDIA H100, for example. Okay. Conditional forward pass, use FP8 is true, and the model, if FP8 is true, and the model is in training mode, self-training. Where is this even showing? Let me see. It uses a custom compiled operation, torch ops operations nano GPT matmul. This operation performs the matrix multiplication in FP8 using predefined scaling factors to manage the conversion to and from FP8. We defined this in my last live. Okay, let's go. If use FP8 is false or the model is in evaluation mode, it falls back to the standard torch NN functional linear operation, ensuring the weight tensor data type matches the input tensors. What? The standard, what is this? The standard is like linear, so I guess BF16 or whatever it is. Okay, so if it's in the evaluation mode, okay. Let me check the code. Actually, custom initialization, it uses reset parameters method that initializes the weights using a uniform distribution with a slightly different scaling factor. Okay. Uh, 0.5 times. I wonder where this is. Let me try to find this in my code here. Okay, here. Reset. Okay, so we got init, in features, out features, use FP8, scaling factors. Okay, in features, out bias. Okay, reset params. What does that do? I forgot. It includes parameters method that initializes the weights using a uniform distribution with a slightly different factor. 0.5 times self-in feature, square root of 1 over self-in features. I don't know. Oh, whatever. Okay. Okay, so in essence, casted linear is a specialized linear layer designed to leverage FP8 computation for efficiency during training when specified, while behaving like a standard linear otherwise. Okay, explain this bound. What is that? Like, I don't know what that is. And this scaling factor. Okay, so that's what we have within this casted linear. I guess we have this forward as well. So if use FPA and is training, then it's gonna use, so it's gonna flatten, okay? Flattening the second to last dimension, I don't know. We're gonna get some out, which is gonna be, this is our custom defined math multiply up. We talked about that in the previous streams. Let me read this. Let's break down the initialization of the reset parameters method of casted linear. Reset parameters self this is the scaling factor calculation. This calculates the bound based on the scaling factor with torch no grad, initializes weights uniformly between minus bound and plus bound. Okay, the scaling factor, STD calculates the desired standard deviation for the initial weights. And then we have this scaling factor, which is 1 over square root of input dimensions. This scaling factor is fundamental to many standard initialization techniques like Glorot, Xavier, and Kaiming. Is it the guy? Initialization. The goal is to keep the variance of the layer's output activations roughly the same as the variance of its input activations, which helps prevent gradients from exploding or vanishing during training. The additional multiplier of 0.5 is an empirical adjustment noted in the code comment. 0.5 is a bit better than the default 1 over square root of 3. Which 3? This 3. No. What? Yeah, this is the square root of 3. Okay, and then hey, I don't know. What is this? Okay. This is square root of 3. But where is this? Where is it? At 0.5 times in features. I don't know what this 3 is, where that comes from even. Okay, let's see. The bound 3 square root of 3 times standard deviation calculates the limits for the uniform distribution. The weights are initialized using self-weight uniform minus bound to bound, meaning they are drawn from a uniform distribution U minus bound to bound. There's a direct relationship between the standard deviation sigma of a uniform distribution U A B and its bounds. I don't know. Okay, why is it even doing this? What are we even trying to do? Okay. What are we even trying to do with this? Okay, I think we need to first figure this out. Oh, this is rotary embeddings. Wait. Based on the train GP, primary goal is to train cast. Oh my god. Okay. Okay. I think I know. This bound. Okay, so this is minus bound to plus bound is. We have FP16 numbers, and we want to condense them down to FP8. But FP8 can only represent a lot fewer numbers. So we need to somehow decide like the upper lower bound of, and then condense values of FP16 within those bounds. Okay, I think that's it. And this is how they choose the bounds, I guess. Y3 to the power. Okay, this is something for another time. Rotary embeddings. I actually explained rotary embeddings a lot in my on my channel. You can check coding DeepSeek from scratch. You can check coding Llama 4 from scratch, and you can check just rope on my channel. So just search the channel for those 3 videos. All of them explain rotary embeddings. Okay, we can skip over this. Causal self-attention. Calculate head dimension based on model dimensions. Okay, give me a second. Give me a second. Okay. Oh, just a second. Okay. Apple cut cross entropy. Let me just check something quickly. Just give me a second. Okay, let's continue here. Calculate head dimension based on model dimensions and number of heads. Okay, I think this is quite simple. All of these are in those 2 videos, DeepSeek and Llama 4 from scratch. Now, what is this standard deviation thing? And bound. Both of them again. So merged query key value weights, suggested by many, implemented by this guy, and further improved. Let me just quickly go to this link URL and check what the bro says. He says, there's a long post. New NanoGPT training speed record. New token-dependent LLM head bias, fused several operations, multi-GPU grad bug fix, steps, decreased number of steps, semi-orthogonal init more in thread. Okay. It's interesting, but I know you don't see it. Okay. Let's just go through it. So query key value weights. Why are they the same? That's crazy. Yeah, they merged it for some reason. Okay, so we merge the weights. Okay, I guess I'm gonna ask here to explain this post. So I'm gonna paste the whole post, explain this, everything the guy posted. Okay. Let's see. This text is a series of posts from someone named this guy. Okay, I know this. New speed record, reproducibility. Okay, token dependent bias. Added a unique learnable bias for each token in the final output layer, LM head. Yeah, that's the output head. So this is the final layer. Each token gets some other bias. I guess bias is a single number. This significantly improved how quickly the model learned data efficiency for this, reducing the required training steps by almost 5%. What? Okay, I'm gonna give it this file. So I'm gonna say explain this token dependent bias, what it is and why and how does it work. Okay, let's see. Why is it planning next move? I should have said ask, not just. Okay. What is it? It's a learnable parameter vector associated with the final output layer LM head of the language model. Learnable parameter vector associated with the final LLM. This vector has a unique value, a bias for each token in the model's vocabulary. So if the vocabulary size is 50,000, this bias vector also has 50,000 learnable values. Why? Improve data efficiency. The text states that bias significantly reduces the number of training steps needed from 1,390 to 1,330, meaning the model learned the task faster with less data. I don't know. But they are just measuring the loss. So can we trust that if loss is the same, that the model is same? I will trust it for now. Maybe they know the rules when that applies, so they apply the rules properly. I will trust. Okay. Direct logic adjustment before the final softmax function turns the model's raw outputs into scores, probabilities, output scores into probabilities, probability distribution. This bias is added. It gives the model a direct way to increase or decrease the baseline likelihood of predicting any specific token. It seems like a why. Like why? Independent of the current context processed by the transformer layers. Some tokens are inherently more or less common, and the bias can help capture this base rate. I don't like this. This is just like how common tokens are in language, as opposed to like using actual reasons to solve the task, generating tokens based on the task and based on solving the task or the prompt. But this is just generating tokens based on how common they are in language. So, but maybe it's okay. I don't know. Computationally efficient alternative. The text or actually this could also be a speed up. Maybe somehow this just helps the LLM if the token is correct to find it faster. I don't know. Without compromising on quality. I don't know. Computationally efficient alternative, the text contrasts with logic biases, which might refer to more complex or computationally intensive methods of adjusting output probabilities. This token-dependent bias is likely just a simple vector addition, making it relatively cheap to compute. I think it is just a simple vector addition. How it works conceptually? Normally, the final step in the transformer before getting probabilities is final hidden state, okay? Linear, so this is the output head, and it generates logits. With the token-dependent bias, it becomes final hidden state, output head, raw logits, and final logits are equal to raw logits plus token bias vector. Token bias vector has a single number for each token, and this is a list of logits for each token, so they just get added for each token. Element-wise addition, potentially broadcasted. Then probabilities is softmax of final logits. That is such a hack. Okay. The token bias vector is learned during training via backpropagation. Just like the weights in the linear layers or attention mechanisms. Yeah. The model adjusts these bias values to maximize the prediction error loss. I wonder, like, what would this do? It's independent, maybe. No, I don't know what this does even. Important note on the provided code. Based on the trained GPT-Pi code you attached, the LLM head is defined as a casted linear layer. So that's It supports FP8 is what it means. Okay. Looking at the casted linear class definition, it inherits from NN linear, but explicitly calls the superclass init with bias false. Okay. In the GPT forward method, the output of self LM head is directly used after scaling without adding an explicit bias vector. So are we not adding this thing that this guy? Therefore, the specific implementation of the token-dependent bias described in the tweet does not appear to be present in the version of the train GPT. Okay, let me ask. Okay, let me just ask. Oh my God. Oh, okay. I don't know. Maybe Evan removed this. I don't know. Let me just send him a message. Did you remove this token bias, token vector output head bias thing? Okay, let's go. The tweet mentioned lots of scattered little changes. So this feature might have been implemented differently, perhaps directly modifying the casted linear or adding a separate parameter. But I think if it is implemented, then this AI would be able to figure it out. And maybe it's not implemented. Okay. The second improvement, residual subtraction and noisy embeddings. They subtract the initial input x0 from the residual connections and add noise, controlled by a schedule. What? To the embeddings early in the network. Why? These changes, partially inspired by the work, improve performance and robustness. How? Okay. So what do they do? Subtract initial input from the residual connections and add noise. What? Okay. Let's just keep that somewhere in the back of my mind. Maybe I'll look into that later. Semi-orthogonal initialization. Use the specific method to initialize the model's weights to be semi-orthogonal. Okay, this guy. Hello. Let me check my link. Okay. Just checking messages. Okay, use the specific method to initialize the model's weights to be semi-orthogonal, which can improve training stability. Model weights to be semi-orthogonal. Model weights to be semi-orthogonal. Wait. This is, we are using muon optimizer, and this is already creating orthogonal updates, so orthogonal gradient matrices. And this is making a weight semi-orthogonal. Okay, we'll figure it out. I don't know. Fused operations. Combine multiple computational steps into a single fused operation, which generally speeds up computation on GPU. Do you see any fused operations here? Okay, this is the first question I will ask, but later. Let me add more questions here as we read. Generalized RMS norm scalars added learnable scaling factors to all RMS normalization layers. Learnable scaling factors to all RMS norm layers, inspired by this guy's query key norm, improving performance and speed compared to other methods. Multi-GPU bug fix. Corrected an error where the training loss wasn't properly scaled when using multiple GPUs. This fix ensures consistent results regardless of the number of the GPUs used. Okay, the second question is explain in more detail the generalized RMS norm scalars. Those are going to be our two questions. Okay, I think it's answering. Let's see. Actually, I like Gemini 2.5 Pro. I think this is the best model. I'm using that model every time. I don't know about 04 Mini now. It's not available yet. So let me just check quickly. So is 04 Mini available here in this guy? Why can I not check? So if I go thinking, I don't see it. Yeah, I don't see it. Okay. Yes, there are several places where fused operations are likely used or explicitly requested. Adam optimizer. The Adam optimizer initialized with fused equals true. Okay, let me see. So we have this Adam optimizer, fused equals true. I'll just get this for later, this URL. There are so many URLs here. Setting fused true tells PyTorch to use a more optimized kernel that combines multiple operations like calculating updates, applying momentum, and updating weights into a single GPU launch, reducing overhead and potentially increasing speed. Custom FP8 kernels. Yeah, these are, wait, they are, what? Now, I don't really understand if these are like kernels. Maybe they are. Then it would be, I don't know if these are kernels though. I mean, it says they are, so they are. While not standard PyTorch fused ops, the custom FP8 matrix multiplication operations defined using Torch library custom operation are essentially hard-written fused kernels. They leverage Torch.scaled math multiply, which itself performs a scaled matrix multiplication, potentially fusing as scaling the scaling and math multiply, fusing the scaling and math multiply. The backward pass also fuses gradient calculations. Okay, we have Torch compile. So are these actually kernels? Explain kernels. Okay. Okay, what else do we got? We got one of the primary optimizations Torch compile performs is operator fusion. It analyzes the computational graph and automatically merges compatible sequential operations like activation functions, normalizations, element-wise operations into single, more efficient kernels where possible. For example, ReLU X square sequence in the MLP block is a prime candidate for fusion by the compiler. Flex attention. The use of flex attention is another form of fusion. It's a specialized kernel designed to handle attention calculations, including masking and scaling, efficiently, particularly for block sparse patterns. Block sparse patterns, replacing multiple separate operations. Okay. Generalized RMS norm scalars. The tweet mentions we add an update to the RMS norm operation that generalizes these guys learnable query key norm scalars, but for all RMS norms. This version appears to be much speedier than having a unique scalar per channel. So per channel, I'm guessing per embedding. So in the token embedding, there is a bunch of numbers. Each number in the token embedding is a channel. I'm guessing, it's what I'm guessing. Let's connect this to the code. RMS norm basics. RMS norm root mean square normalization normalizes the activations within a layer based on the root mean square of their values. Means, so you calculate mean, you square it, and then you find root. It's a computationally simpler than layer norm. Standard RMS norm rescales the normalized outputs by a learnable single scalar gain. Element-wise, a fine true in NN RMS norm. Per channel, scalars would imply a learnable gain vector applied element-wise. So you have the vector that's applied. So the length of the vector is same as the length of the entire token embedding. And I'm guessing that same vector is applied to every token. Same vector for every token. And it's same length as every token. Token embedding is what I'm trying to say. Okay. QK query key normalization. The code does implement query key normalization attributed to this guy. Who likely adopts this guy's idea? Okay. So we got some inside causal self-attention forward. Linear layer. How is it? Wait. No, I don't understand. Norm. Okay, so apply normalization to Q and K. Yeah. Okay. Okay. And then rotary embeddings to query and keys, and that's it. I just don't get this line though. Let me try to find it. Maybe if I see the whole line, I'll get it. Okay. Oh my God, what is that? We have this linear layer. Input is the tensor X. And then we say Q value weights flattened something as type X. And then view batch time or sequence length 3 times self number of heads, self head dimension. Oh my God, what is this? I guess this whole matrix query key value contains all query conversion matrix, key conversion matrix, and value conversion matrix just concatenated. So 3 in 1. And then we divide it here. That is, I think we multiply this X with all 3 separately and get query key and value. That's what I'm thinking happens. Here, norm is defined as f.rms norm. This applies RMS norm independently to the query Q and key K vectors before applying rotary embeddings. Okay, we know this. Pre-block normalization. The code also applies RMS norm to the input of both the attention block and the MLP. Okay, so RMS norm is before attention block and before MLP block. Let's check the code. If self-attention is not none, X is the residual connection. Okay, and then you pass into self-attention, but first normalize. And so in the self-attention, you pass in this normalized input, RMS norm input, and this is value embeddings. This is separate thing that you just add to every value vector. It's something. And block mask, this is because we are not using batches. I think we are just using everything like documents that are like we just concatenate every sequence into one big batch, and then you need block mask to just mask all of the other sequences in that batch, except the currently processed sequence. And this value embedding, so every token is going through the layers of the transformer, and its value vector is constantly evolving. And the deeper you go into levels, into layers, the more this value vector is different from the initial value vector the first time it's created. So the first time it's created, it's just like input token converted to a value vector with some matrix. But as you go, it gets changed. So we have this new thing, value embedding. So this is going to be converted. This is going to be added to every value vector. Maybe not every, actually just in the first 3 layers and last 3 layers. And this is created from the initial embedding, initial token, just converted with some matrix to this value embedding. So it preserves a lot of information of the initial embedding. Hi, I'm from Cyprus. Have you encountered some hallucinations in the AI explanations? I am somewhat worried about myself embracing LLMs for learning, worried it will BS me here and there, and I couldn't know when it's BSing. So the way I do it, you just read and try to, I think it will not hallucinate too much. I think because this is something that's already explained on the internet, so it's good at these things where it already learned like this kind of stuff. And if it hallucinates a little bit, even if you learn a little bit wrongly, you will correct it later. But you will not. Maybe you will learn like sometimes, very rarely, something wrong. But it doesn't happen because I don't think you will learn anything wrongly, because it's the idea is complex. So you need to look at it from many perspectives in many ways. So even if one of those ways is not like doesn't make sense or is wrong or hallucinated, you'll notice. Let me take off my shirt. Yeah, you'll notice, I think. So I'm not really worried about them hallucinating. Okay, let's see. Generalized interpretation. The code uses norm. Yeah, this RMS norm, which is functional, which is the functional version. What does it mean? This version does not inherently include a learnable element-wise affine gain parameter like the RMS norm. I don't know what this is, by the way. There are no separate learnable scalar parameters associated directly with the norm calls in the block or causal self-attention modules in the provider code. Conclusion. It seems the generalized RMS norm scalars mentioned in the tweet likely refer to the consistent application of RMS norm at multiple points, query key norm, pre-attention norm, pre-MLP norm, potentially building on the query key norm ideas. The tweets contrast with per-channel scalars suggest they stuck with the standard RMS norm approach, which implicitly has a single scaling factor, even if not explicitly learnable in the FRMS norm implementation shown. Oh my God, I don't know what I'm reading. Let's go next one. Okay. Yes. Okay. Let's see. Are these actually kernels? Explain kernels. Yes, the fused operations and custom operations we discussed absolutely involve GPU kernels. What is a kernel in GPU computing? Think of a GPU kernel as a small program or function that is specifically written to run on the GPU's parallel processing units cores. Your main Python code runs on the CPU. The CPU acts like a manager when it needs to perform a heavy parallelizable computation, like matrix multiplication, convolutions, or the operation within an optimizer step. It tells the GPU what to do. The task. The specific task the CPU assigns to the GPU is defined by a kernel. The kernel contains the instructions that each of the many GPU cores will execute. So kernel is contains the instructions, often simultaneously on different pieces of data. Thanks for the response, no problem. You're welcome. Parallel execution. A single kernel launch can trigger thousands of threads on the GPU, each executing the kernel code on a small part of the overall problem. This massive parallelism is why GPUs are so fast for tasks like deep learning. Example, a kernel matrix multiplication would contain the instructions for calculating a single element or a small block of elements of the wait. A kernel for matrix multiplication would contain instructions for calculating a single element or a small block of elements of the input output matrix. So I'm guessing you just instruct the LLM or whatever the kernel how to calculate each parts of the matrix and then combine them all together in the end. Okay. A kernel for ReLU activation would contain instructions to apply the max of 0 and x function to an element. Okay. Standard PyTorch operations, linear, ReLU, RMS norm, etc. When you call these functions on GPU tensors, PyTorch doesn't run a Python code on the GPU. Instead, it selects and launches highly optimized pre-compiled GPU kernels, often written in CUDA C++ and part of libraries like cuBLAS, cuDNN, and PyTorch own backend to perform the calculation. Fused operations. Fuse true, Adam, torch compile out. What is this? When operations are fused. Okay, we read this. Yeah. Okay, wait. When operations are fused, PyTorch or the compiler doesn't just launch the individual kernels for each original operation, one after another. Instead, it generates a new single kernel that combines the logic of those multiple operations. Launching one combined kernel is much more efficient than launching many small ones sequentially because it reduces the overhead of communication between the CPU and GPU and can optimize data movement within the GPU. Okay, custom FP8 kernels, we got these two. These are explicitly defined custom operations. The underlying implementation, torch scaled MM, and the logic within torch compile calls specific GPU kernels designed for FP8 matrix multiplication. These might be kernels provided by NVIDIA libraries or, okay, wait. These are explicitly defined custom operations. The underlying implementation, scaled MM, and the logic within torch compile call specific GPU kernels designed for FP8 matrix multiplication. These might be kernels provided by NVIDIA. Okay, so it just calls these kernels. Okay, flex attention. This is a direct call to a specific highly optimized GPU kernel provided by PyTorch designed for flexible attention patterns. So this whole thing is a kernel or what? No, not the whole thing. I guess there are a bunch of defined kernels here. Okay, I think that's it for kernels. Maybe we understood something. So where were we? I guess MLP, no. Casted linear rotary. Okay, let's see. This forward layer, this is from the causal self-attention. What is this? Okay, we already maybe got through this. So let me check this. Must use batch size of 1 for flex attention. Flex attention. I think we got through this, yeah. This is the vector value embedding that I was explaining. We add these values to the first. Skip mid layer tokens value. Yeah, this is the first n layers. We add the value embeddings, and the last n layers, I guess, and then skip mid layers. I don't know. I'll figure this out later. I don't know what this is. Scale the attention logits by given constant instead of the default head dimension, 1 over square root of head dimension. Inspired by learnable scalars used by this guy in this tweet that we read about. Flex attention Q transpose, K transpose, V transpose. Why do you need why do you need Q transpose? Okay, it is what it is. It is what it is. Reassemble all head outputs side by side. Yeah. I guess this is yeah, flex. So we just call this flex attention. We just like call this and that's it. And then it does. So we don't implement attention by ourselves. Okay, let me ask Evan. So I see that we don't implement attention ourselves, just use flex attention. Are there possibilities for optimizations if we do it ourselves? Okay. MLP block. Let me see. We are failed. Okay. Casted linear. Forward. I mean, this MLP block, this just linear layer, activation function, and linear layer. Okay. 1-2% better than Gelu, suggested by these two dudes. So it's Relu squared. Okay, I guess it's just okay. Let's see the block. Skip attention of blocks 7, the 8th layer. What? Why? Adjusted for smaller models. Only skip if we have enough layers. Skip attention for why? What? Only why? Let me ask here. To check why is it skipping attention for layer 7? Okay, while that's going on, we have attention mechanism, dimension, head dimension, max sequence length. If not, skip attention, else none. Okay, MLP dimension and MLP ratio is just so you know MLP has input, middle layer, and output. These three, and this middle is like the ratio. So if you have input and you have ratio 4, the middle will be 4 times the input, middle layer. Self lambdas, if I only knew what these lambdas are. What are these lambdas? Let me edit. What are these lambdas? Lambda's parameter is a learnable tensor that controls the weighting of the skip connection of the block. So residual connection weight. It determines how much of the original input x0, the transformed input x, contribute to the final output, and the transformed input x contribute to the final output. What? It determines how much of the original input x0 and the transformed input x contribute to the final output. Really? Okay, I'll just, I don't know. Okay, what is this? Let's edit. Explain this lambdas of 0. Let's see. The lambdas parameter is a learnable weight that balances the contribution of the input tensor x and the initial tensor x0 lambda 0 scales x. So okay, wait. The lambdas parameter is a learnable weight that balances the contribution of the input tensor x, input, okay, and the initial tensor. What is initial tensor? X0, lambda 0. Lambda 0 scales x, while lambda 1 scales x0. What is x0? X0 is, I'm guessing, like the output of the first block, or I don't know. This allows the model dynamically adjust the influence of the current and initial states. Input tensor. Wait. So x0 is the input to the transformer, and x is the output of the last layer. In this context, x0 represents the initial input to the transformer block, while x is the output from the previous layer, or the current state of the input as it passes through the network, okay? The lambdas parameter is a learnable weight that balances the contribution of x and x0. Lambda 0 scales x, which is the output of the last layer, and lambda 1 scales x0, which is the original input to the transformer block. Okay. This mechanism allows the model to dynamically adjust the influence of the current and the initial states, providing a form of residual connection. Okay. Save it. The main model. Let's go. Okay, next multiple of n. Okay, yeah, this is just gonna find the next multiple of n. So this is actually very, very simple. If you have number 7 and you want next multiple of 3, it's gonna return you number 9, because 9 is the next multiple of 3 after 7. GPT. Model dimension, this is the vector embedding dimension, I think. Max sequence length and lookup size. Yeah, this is the big vector, the big embedding matrix that has lookup size times. So this is embedding for each vocab token. Token value embeddings. Yeah, this is, I already talked about this, I think. Yeah, we have Y3 though. Yeah, maybe we have 3 layers. So this is to preserve value of the initial vectors, tokens that in the beginning where they were just inputted into the transformer. So we want to preserve their information. So we will just add these later to whatever we get processed. This is number of blocks. So this is the blocks. So create a block from attention mechanism and MLP and RMS norm and stuff. So there is only 50,000 unique GPT-2 tokens. We extend to nearest multiple of 128 for efficiency. This originates from Karpathy's experiments, and it's true. You want to have multiples of 128. LM head, this is the big block in the end. Casimir. Model dim, next multiple of 128. Whatever. So we will just this matrix that contains vector embeddings for each token. We will just expand it so it has multiple of 128 vectors, and the additional vectors, I think they will just be like zeros or something. I don't know. So they will be ignored. Okay, add learnable skip connection weights for decoder layers. Number of layers must be even for skip connections. Okay. I don't know what this is. What is this? Oh, why did it change? Oh, yeah, yeah. If number of layers is not 2, then we need to, if number of layers is not an even number, then we need to make it an even number. Okay. Sliding window num blocks is tensor of shape W. What is this? This is forward for the GPT. Input sequence, number of dimensions is 1. What? Okay, we just get these value embeddings. This is creating flex attention mask here. Yeah, this is flex attention mask. Sparsity pattern is independent of batch and heads. We'll set them to none. Okay, UNet design. Why UNet design? What is this? Okay, I'll just tell it. Add explanation comments. Initialize a list to store skip connections for the UNet design. Initialize a list to store skip connections for the UNet design. Determine the number of skip connections based on the length of. Why do you need UNet, by the way? What is the UNet used for and why is it needed? Okay. I want to reject this, by the way. Here's what I'll do. I'll just ask this guy on the side to explain this stuff. Add to chat and say explain. Okay. It's thinking for a little bit. Okay, UNet style skip connections. This part implements skip connections inspired by UNet architecture. Length of skip weights gets the number of skip connection weights, which is half of the total number of layers. The code iterates through all the transformer blocks. First half, encoder like. For the initial n layers, the output x from each block's I is saved into the skip connections list. Second half, decoder like. For the remaining layers, I is greater or equal to n. Before processing the input x with the current block's I, it adds a corresponding output from the first half. It pops the last saved connection from skip connections, matching layers symmetrically. I don't know what I'm reading. Okay, I don't know what I'm reading here. Let's take a look at something. I can't. I don't know what I'm reading. Get number parameters. What is this? This is for generation. Take a conditioning sequence of indices index, long tensor of shape T, and complete the sequence max new tokens times, feeding the predictions back to the model each time. Okay. This is just the generation loop. So I guess our model is finished by 478 line, I think. We have some hyperparameters below. This is the logging. I don't know why we have seed. Seed should be on top. I don't know why it's here. Maybe it's okay. I don't know. Model. Here we are defining the model number. Okay, so it's actually, I thought like the file has 1,300 lines. I'm thinking like the model is huge then, but model finish at like 400 to 500. So it's not that crazy. Okay, experiment. This is all in one file, but I still don't. Okay. Okay. LM head use. Okay. Let's ask. Oh, warm up kernels. What does this do, bro? What does this even do? What does, oh, actually, explain warming up kernels. Bro, I wish you got some real viewers very soon. Thank you, bro. Don't worry about it. I don't know. Just don't worry about it. Don't worry about it. Okay. Okay, let's break down the warming up kernels section. Kernels are just instructions to do some operations together. So if you have times and plus, so you say a plus b times c, instead of doing a plus b, or I guess you would do first times, and then you would do plus after in two separate kernels. This way we can combine them into a single kernel. So we don't need to send memory like in data between different kernels and CPU. We can just do everything at once, so it's faster. So what is warm up? Initial overhead. When you run a PyTorch model, especially using one using Torch compile or custom CUDA operators, for the first time, there's often significant one-time setup overhead. This includes just-in-time compilation is what I think it is. PyTorch might need to compile specialized CUDA kernels tailored to the exact shapes of your tensors and the operations being performed. Specialized shapes of tensors. Memory allocation. The GPU needs to allocate memory buffers for intermediate results. GPU needs to allocate memory buffers for the intermediate results. The very first allocation might be slower. Kernel selection tuning. Sometimes libraries like cuDNN for convolutions, though less relevant here, might try different kernel implementations to find the fastest one for your specific hardware and input size. Performance measurement. If you start timing your training loop immediately, these initial slow iterations would skew your performance measurements like milliseconds per step, making it seem like training is slower than it actually is once everything is running smoothly. How to code warm-ups. How the code warm-ups. It saves the initial state of the model and optimizers. It runs a small number, warm-up steps 10, of complete training iterations using random data, torch randint. This loop executes the core operations: forward pass, backward pass, gradient reduction, reduce all reduce, and optimizer step. This forces PyTorch and CUDA to perform all the necessary initial setup, compiling kernels, allocating memory, etc. Crucially, after the warm-up loop, it restores the model and optimizer states from initial state. Okay, this ensures the warm-up process doesn't actually change the model's initial weights or the optimizer's momentum buffers. It's purely for initializing the Okay, this ensures the warm-up process doesn't actually change the model's initial weights or the optimizer's momentum buffer because it's reset. Yeah. Okay. I guess we get that one as well. Let's see. Training and validation. Okay. What do we have here? We are measuring training time. Calculate average time per step up to this point. Just measuring times and stuff. Okay. So I think Evan doesn't want to separate it. Kind of scared to separate it into different files, but I think maybe we can create another file and then try to separate this, make it more modular. So we can experiment on this better. Because model definition should definitely be in a separate file. How would you make this more modular? I also want to be able to later implement FP8 training, but the file is just too messy and everything is in it. Let's just ask it. Okay, leave that there. I think I'll just let's see my changes, my Git changes. I have some comments added and stuff. Hyperparameters. Wow, I don't think I want to change hyperparameters. FP8 operations contains the custom FP8 matrix multiplication operators. Mu1 optimizer definitely not. I don't think so. Model contains GPT model architecture, including all of this good stuff. This includes data loading, train tokenizer, evaluate, utils, next multiple, train. Okay, the main. Okay, so I think I would want it to just create. Okay, just separate train.py, then evaluate.py and data.py. Others should remain in the same file also. What else? Comment how to use it. I think it's like good enough to do this. I don't want it to change this train GPT though. Okay, so I guess it's creating this. And now this should be a new file, and let's accept it. I wonder if it's gonna work. And then it's gonna create evaluate py. Okay, let's accept it. Vibe coding AI. And then it's gonna modify this, which I don't want to be modified, so I'll just I'll copy it. And after, I'm gonna just save like a copy here, I guess. New file, train GPT big original.py. And now I'll let it modify this. So we have like just the model, and so we have model hyperparameters, muon optimizer, and these things needed for training that we can optimize. It's spending quite some time generating it. I guess let's just wait a little bit more. I hope it's gonna, let's see. Okay, while we are waiting, let me copy this whole thing. Let me ask Gemini, how would you, I'm asking in a browser, how would you accelerate training here? Maybe add apples cut cross entropy, maybe convert to FP8, and other suggestions. Let's see what Gemini says. And then we can accept this, I think. So this is evaluate pi. It's still generating. Okay, let it generate. I'm gonna go ahead and create a new file here, gemini.txt. I'll just show you its response so we can read it together on how to improve this architecture. Once it finishes, which is, it's taking some time to finish. Okay, it started writing. I don't know why this is not doing anything, by the way. Okay, let me see. It wrote finish, not yet. What is it saying? Okay, now I can copy text. Why is my MacBook fan going crazy? Is it overheating or something? Let me check. My MacBook is going crazy. Let me paste this here, the response. So it didn't modify, so I think I need to say, do it, you didn't modify it. Let's see what this guy says. Let's break down potential acceleration strategies for your impressive modded nano GPT script. Let me do this. How do you do this? Yeah, this. FP8 flex attention muon custom data loader unet skips value embeddings, etc. Okay, my MacBook now it's not going crazy anymore. Okay. Expand FP8 usage beyond LM head. I think we already use it beyond LM head. Anyways, current state. Your casted linear supports FP8, but it's only explicitly enabled for LM head based on the Hopper flag. The projections within causal self-attention, C projection, and MLP projections currently use the default F linear, likely BF16 or FP32. It's probably BF16, I think. Opportunity, these linear layers are prime candidates for FP8 acceleration, especially on Hopper plus GPUs where FP8 tensors cores provide significant speedups and memory savings. Implementation. Add flags or modify the Hopper logic to control use FP8 for these layers. Crucially, determine appropriate scaling factors. Yeah, okay. Static scaling, determine good empirical values. Dynamic scaling, implement logic to compute scales based on input weight statistics. More complex adds overhead. A common approach is to use max absolute value over a recent window. Modify the init calls. Okay. Okay, this is just a code implementation. I mean, we can check maybe. Okay. I guess we will do this first for efficiency reasons and then. Wait. Okay, trade-offs. FP8 significantly reduces memory and computation, but introduces quantization error. Careful scaling is essential to maintain model quality. Test convergence and validation loss rigorously. Okay, Apple's cut entropy loss, candidate sampling. Concept. Cut cross entropy and similar techniques like noise, contrastive estimation, or sample softmax approximate the full softmax loss over a large vocabulary by computing the loss only on the true target tokens and a small subset of randomly sampled negative incorrect tokens. This drastically reduces computation and memory bandwidth for the final LLM head layer, which can be a bottleneck with large vocabularies. Vocabulary applicability is highly relevant here. Yeah, you need a library or implement it yourself. Apple released reference implementations, often in TensorFlow or JAX. Ports might exist. Search for PyTorch implementation of sample softmax, candidate sampling loss. Let me just quickly search if this is what I need to search. Okay, let's keep reading. Replace F cross entropy in the GPT forward method. Requires cut cross entropy implementation. Cut cross entropy library import cut cross entropy loss. Okay. Torch compile tuning, that's the next optimization idea. Opportunity mode max autotune can potentially find faster kernels, especially for compute-bound operations like matrix multiplication at the cost of longer initial compilation time per graph break. Okay. Implementation change torch compile model dynamic false, reduce overhead, to model dynamic false, max autotune. Maybe we don't need this, I don't know. I'll just why not use this? I'm gonna ask Evan. Max autotune for torch compile. Okay, let's continue. Inductor backends. The commented out torch inductor config max autotune whatever suggests potential experimentation. Default inductor tries Triton and C++ backends. Limiting it might be necessary for specific bugs or performance issues, but generally letting it explore options, CUDA graphs, Triton, attention. Okay. Explicit mix precision with torch amp autocast. Current state, the script seems to rely on input types and specific layer casts, BF16, FP8. Okay. Opportunity use torch amp autocast provides a more standard and potentially comprehensive way to enable mixed precision. BF16 in this case, as FP16 isn't used. Profiling, this is crucial. Before heavily modifying FP8 scaling or implementing cut cross entropy, profile your training steps to identify the actual bottlenecks. Tools, Torch compiler, can show CPU, GPU time, operator breakdown, memory usage. Okay. Okay. And then we have minor optimizations checks. Muon zero power via network, Newton-Schultz 5. Gradient checkpointing if memory becomes a constraint, especially with large model sequences. Consider torch utils checkpoint for selected blocks. Okay, I think I understand it. Maybe I read it, I guess. So here we got a new version of Train GPT. It's gonna be a lot smaller, maybe, I don't know. Yeah, it's gonna be smaller. Accept 5. It's not even that smaller though. Okay, I think I'm gonna go onto a pause a little bit. I'm gonna go onto a bro. What things I have to learn to contribute to open source? I can see your comments. I don't know. We need to. It's tough. You need to learn everything I'm learning right now. That's what you need to learn. Just like go to this repository and learn. I guess I don't know. Okay, let me just write like a 10, or let's say like 10-minute pause, and I'm just gonna leave it here. How do I zoom? Like this. Okay, I'm just gonna come back in like 10 minutes. Okay. I'm back. Okay, now what do I want to do? What do I want to do? Is my mic muted here? No? Okay, LinkedIn not. Let me close my window. Okay, I wonder what we want to do next. Maybe let's check Apple's paper. Apple's paper. I want to maybe share the whole screen now. Let me first reset this size. Okay, so I'll go ahead and share whole screen on YouTube. I need to stop sharing, I think, first. And then entire screen capture. Okay, my LinkedIn. How do I share this here? I guess I go display capture. Okay. Now it should be sharing this whole display on LinkedIn as well. Okay, what is this? Primer, searching for efficient transformers for language modeling. What is that? Okay. I see stuff. I guess what I can do is copy all of this and tell this guy to explain. And while that's explaining, I think this is the one that we want. So this is Cut Your Losses by Apple. Maybe we want to implement this. Let me just make sure everything works okay. Okay. Explain. Let's see what this guy says. Transformer models are incredibly powerful. Oh my God. The goal to find more computationally efficient variant of the transformer architecture, specifically for autoregressive language modeling, like GPT. Efficient here means achieving the same or better quality, example, lower complexity with less training and compute. I don't know why my MacBook is getting overheated again. The approach, instead of searching over high-level design choices, like which type of attention layer, the authors took a lower-level approach. They defined a search space consisting of basic TensorFlow programming primitives, fundamental operations like addition, multiplication, convolution, simple activations. They used evolutionary search, specifically regularized evolution, to explore this space. Models are represented as DNAs, which define TensorFlow programs. Models are represented as DNAs, which define TensorFlow programs, specifically the decoder block. A population of models is maintained. Models are evaluated based on their fitness, how low a validation perplexity they achieve within a fixed compute budget. Okay, better models are selected, mutated, small random changes to their the TensorFlow program structure operations, and the process repeats. Maybe this is something we can do. Maybe this is something we can do, like evolutionary parameter or hyperparameter exploration. Okay, let me just check my screen, my streams. Okay. Conceptual. No. Okay, the results. Primer What is this? Easy. I don't know. The search discovered an architecture they named Primer, primitive searched transformer. Analysis showed that most of Primer's benefits came from two simple key modifications compared to the standard transformer: squared ReLU activation in the feed-forward network, part of the transformer block. Instead of using the standard ReLU, they used a squared ReLU. Okay. That's how they discovered the square ReLU that we are using. This simple change proved highly effective. And then multi-deconv had attention, multi-convolution, whatever. After projecting the input to get the query, key, and value matrices in the multi-head self-attention mechanism, they add a small 3x1 depth-wise convolution layer over the sequence dimension for each head independently. So how does this evolve? How did it evolve to squared ReLU? Was it human coded or automatic somehow? Okay, key findings: improved training efficiency. Primer consistently reaches target quality levels using significantly less training compute than standard transformer, vanilla plus GELU, across various setups. Example, at 500 million parameters, Primer achieves the same quality as the original T5 using 4.2x less compute. I don't think you need to do PhD to do research. It's too much effort, no need. It's good if you can, but I don't know. By the time you do PhD 4 years, maybe we're gonna have AI researchers anyways. Example, at 1.9 billion parameters, GPT-3 XL-like setup, Primer achieved similar pre-training perplexity and one-shot downstream tasks performance using 3x. Okay. Robustness, different model sizes. The implementations were observed across different model sizes from 20 to 1.9 billion parameters, different compute scales, different data sets, hardware, etc. I guess they trained a lot. Scaling benefits: the compute savings offered by Primer increased as the total training compute budget grew. The savings followed a power law relative to model quality. Inference benefits: although optimized for training, Primer also shows potential for improved inference. Okay. Significance and takeaways: simple changes, big impacts. Surprisingly simple. Okay, I'm just checking my chat. Surprisingly simple, low-level modifications, squared ReLU, depth-wise convolutions in attention can yield substantial efficiency gains in large language models. New search strategy: searching over low-level primitives with an efficiency-focused objective. Fixed compute budget: searching over low-level primitives with an efficiency-focused objective. Fixed compute budget is a viable and effective way to discover better architectures. How would we do this? Okay, I'm gonna copy our architecture, and I'm gonna tell it to design like an experiment that's gonna search. Now design these experiments that will search for more efficient architecture improvements of our nano GPT architecture. Okay, why does it not let me run, by the way? What? We have a solution here, I guess. Let me go here, paste that. Also gonna paste this entire, so that's it. Put it there and then run this. Let's go back. Okay, so how does this evolve? How did it evolve to square ReLU? Was it human decoded or automatic somehow? It was automatic, found by the evolutionary search. The key point is that the square ReLU wasn't explicitly coded by a human as a specific hypothesis to test. Instead, it emerged as a result of the automated search process combining basic building blocks. Here's how it likely happened. Let me just check, okay? Initialization. The search started with a population of models based on the standard transformer population of models. This initial transformer program contained a subprogram like a function for the activation function within the feed-forward block. Wait. This initial transformer program contained a subprogram like a function for the activation function within the feed-forward block. This subprogram initially implemented the ReLU, like using the max primitive output, TensorFlow math maximum input 0, primitives available. The search space defined by the researchers include basic mathematical operations as primitives, crucially. Max used for the initial ReLU, square, okay. So mutation, the evolutionary algorithm works by taking existing successful programs, parents, and applying small random changes, mutations, to create new candidate programs, children. Several types of mutations could lead to squared ReLU. Instruction, insertion. The most direct way this could happen is if the mutation process randomly decides to insert a new instruction after an existing max instruction within the activation subprogram. If this new instruction was chosen to be the square primitive, and its input was set to be the output of the max instruction, you'd get. It's too complex. Okay, but we know. It just, in short, humans define the menu of possible operations, the primitives like max, square, add, conv, etc., and the rules of the game, evolutionary search, optimizing the complexity under a fixed compute budget. The evolutionary algorithm then automatically explores combinations of these primitives through mutation and selected the ones that worked best according to the rules, eventually discovering the square ReLU structure. Okay, so is this the cut entropy loss? Yeah, cut your losses in large vocabulary. So this is by Apple. This is gonna save like a lot of memory. I heard like third of memory, GPU memory for small models. LLMs are getting bigger. Models have more parameters, longer context windows, and importantly, larger vocabularies, more unique tokens. Vocabulary size, memory bottleneck. During training, LLMs use gross entropy loss. Yeah. The key step involves calculating logits, a score for every possible next token in the vocabulary for every position in the input sequence batch, the logit matrix. This creates a massive intermediate matrix of size number of tokens in batch n times vocabulary. Oh, yeah, so you have vocabulary times embedding length. It's a huge matrix in the end. The modern models with large n, due to long sequences and large batches, this matrix becomes enormous, yeah. Dominating memory usage. Storing this logit matrix in the GPU's main memory, DRAM, becomes the single biggest memory consumer during training, often using far more memory than the model parameters, gradients, or activations combined, as shown in figure 1a. So let's go to figure, figure 1 should be here. I can't find it, let's go back. Okay, existing optimizations weren't enough. Techniques like zero, 4 parameters gradients, activation checkpointing, and flash attention for attention layers have reduced memory elsewhere, making the cross-entropy loss bottleneck even more prominent. The proposed solution cut cross-entropy. The authors propose a new way, okay. So how cut cross-entropy works? Reformulation. They look at the cross-entropy loss formula. Loss is equal to logit correct token minus log sum what? Well, what is this? Logit correct token, the score for the actual ground truth next token, okay? A normalized, and then this log sum exp all logits, a normalized term calculated over the scores of all possible vocabulary tokens. Okay, key insights. You don't need the entire number, whatever, the entire big matrix, logit matrix stored simultaneously to compute this loss or its gradients. The first term only needs the logit for one specific token, the correct one, per sequence position. The second term, log sum exp, is a reduction across the vocabulary dimension. It can be calculated incrementally or in blocks. Custom kernels and SRAM. They implement custom CUDA kernels using Triton for easier development that performs the necessary calculations cleverly. Indexed matrix multiply forward. Okay. To get a logit correct token, a kernel fetches only the relevant input embedding and the specific column from the classifier matrix corresponding to the correct token into the GPU's fast on. A kernel fetches only the relevant input embedding and the specific column from the classifier matrix corresponding to the correct token into the GPU's fast on-chip SRAM, computes the dot product, and writes the single result. No large matrix is stored in main memory DRAM. Okay. Linear log sum exp. To compute this, another kernel processes the input embedding E and the classifier matrix C in blocks. It computes blocks of logits. These within SRAM performs the log sum exp reduction within the block, and then combines the results from different blocks using atomic operations to get the final log sum exp, while a value for each token, again without storing the full matrix in DRAM. Algorithm 2, figure 2b. Algorithm 2, figure 2b. Figure 2b. Can I find it like this? No. Okay. Figure 2b. This one, I guess. I don't get this, bro. This is tough. I don't get this at all. It is what it is. Backward pass gradients. The backward pass also requires computing gradients based on the softmax probabilities derived from the logits. Okay, let's check the benefits here. I don't understand this. I need to think this needs hours and hours or days to understand. Maybe throughout the future we'll understand it. Massive memory reduction. The memory needed specifically for the cross entropy logits drop from gigabytes. For example, 24 gigabytes from Gemma 2b to megabytes, 1 megabyte. Lol. What? The total memory for the classifier head is also dramatically reduced from 28 gigabytes to 1 gigabyte. Larger batch sizes, because memory usage is so much lower, you can fit significantly larger batch sizes, more tokens onto the same hardware. Figure 1 shows 1.5x to over 10x increase. This can improve training efficiency and throughput. Competitive speed, despite avoiding the standard large matrix multiplication, the custom kernels and optimizations, especially gradient filtering, make cut cross entropy as fast as or sometimes slightly faster than standard PyTorch implementation, even compiled ones. No loss of accuracy. The gradient filtering threshold is chosen carefully based on numerical precision, ensuring that the training process and final model convergence are not negatively impacted. Okay. 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 Let me switch back. Just a second. Okay, we're done with this. I guess if I want to understand it better, I'll have to make a video or something. I don't know. Okay. Let me go to my YouTube stream, and I'm gonna stop sharing it here at this point. Okay, let me find. Let's take a look at the newest papers. So I'll go into AI timeline by ByCloud and find the latest papers. Okay, let me put it into here. Let me return to sharing. Let me share my entire screen. Let's go to OBS. This is for link. Display capture. Okay. Okay. So these are the latest papers. I guess, what is this? Let's check this one out. Efficient and reliable reinforcement learning for advanced reasoning tasks. Crazy. ByteDance. How many authors, I wonder? Okay. So what does it say? I think I should. We have project lead, algorithm infrastructure, supervision, affiliation. This university is everywhere, by the way. at so many Chinese papers. Okay, explain. Maybe we can take a look at the abstract. We present VAPO, value model based augmented proximal policy optimization framework. I'm trying to follow it for reasoning models. A novel framework tailored for reasoning models within the value model based paradigm. Benchmarked the AMI, this is the hard one, yeah. 2024 dataset. VAPO built on the Quen32B pre-trained model attains a state-of-the-art score of 60.4 in direct comparison under identical experimental settings. VAPO outperforms the previously reported result of DeepSeek R10 Quen32B and DAPO by more than 10 points. That's a lot. And this is super tough, I think, math dataset. Let me just check if my streams are working well. I think they are. LinkedIn also doing well. I think it's so far. What the hell? The training process of VAPO stands out for its stability and efficiency. Stability and efficiency. Okay. It reaches state-of-the-art performance within a mere 5,000 steps. State-of-the-art with just 5,000 steps. I just wonder how much like one step takes time. I mean, if it's 1 second to 1 minute, it's okay. Moreover, across multiple independent runs, no training crashes occur, underscoring its reliability. This research delves into long chain of thought reasoning using a value model-based reinforcement learning framework. We pinpoint 3 key challenges that plague value model-based methods: value model bias, the presence of heterogeneous sequence lengths, and the sparsity of reward signals. Through systematic design, VAPO offers an integrated solution that effectively alleviates these challenges, enabling enhanced performance in long chain of thought reasoning tasks. Okay. So we have a figure 1. AMI 2024 scores of VAPO on Quen32B base model demonstrates significant superiority over the previous state-of-the-art SOTA method DAPO, achieving this with notably fewer training steps. The x-axis denotes the gradient update step. So we have R1 distilled Quen32B, I guess this one, and then DAPO this one, and then VAPO is crazy high here. And average is 32. Okay. So they try 32 times, and this is the average. I mean, that's okay. That's okay. So I already see this says nothing. In large language models, reinforcement learning training, value-free model methods like GRPO and DAPO have demonstrated remarkable effectiveness. These approaches eliminate the overhead of learning a value model, instead computing advantage solely based on the final reward of the entire trajectory. The trajectory level. So I think GRPO is computing reward based on 8 of them or 6 of them relative to each other, how they performed something. Okay. The trajectory level advantage is then directly assigned as the token level advantage for each position in the sequence. Token level advantage. Let me check my streams. Okay. No messages there. Okay. When training a reliable value model, when training a reliable value model is particularly challenging. Value model-free methods deliver an accurate and stable baseline for advantage calculation by averaging the rewards across multiple trajectories within a group. This group-based reward aggregation mitigates the need for explicit value estimation, which often suffers from instability in complex tasks. Consequentially, value model-free methods have gained significant traction in addressing difficult problems such as long chain of thought reasoning. With substantial research efforts, okay, whatever. Despite the notable success achieved by the value model-free method, DeepSeek R1 GRPO, we argue that value model-based approach possesses a higher performance ceiling if the challenges in training value models can be addressed. Okay. First, value models enable more precise credit assignment by accurately tracing the impact of each action on subsequent returns, facilitating finer-grained optimization. Okay. This is particularly crucial for complex reasoning tasks where subtle errors in individual steps often lead to catastrophic failures, and it remains challenging for model optimizing under value model-free frameworks. Secondly, the contrast to the challenging, in contrast to the advantage estimates derived from Monte Carlo methods in value model-free approaches, value models can provide lower variance value estimates for each token. Wait, what did I read? What did I read? Secondly, in contrast to the advantage estimates derived from Monte Carlo methods in value model-free approaches, value models can provide lower variance value estimates for each token. Okay, so value models can be more precise if they are done well. They are more difficult to do, but they can be better if they are done well, thereby enhancing training stability. Furthermore, a well-trained value model exhibits inherent generalization capabilities, enabling more efficient utilization of samples encountered during online exploration, enabling more efficient utilization of samples encountered during online okay. As the agent is learning, the value model, if it's done well, it can provide more accurate scores and rewards for the agent, for the AI or LLM that's learning. It can be more accurate, better scores, but it's harder to do. This significantly elevates the optimization ceiling of reinforcement learning algorithms. Consequently, despite the formidable challenges in training value models for complex problems, the potential benefits of overcoming these difficulties are substantial. Okay. However, training a perfect value model in long chain of thought tasks has significant challenges. First, learning a low bias value model is non-trivial given the long trajectory and the instability of learning value in a bootstrapped way. So I guess instability of learning value by itself. I don't know. Second, handling both short and long responses simultaneously is also challenging, as they might exhibit very distinct preferences towards. Okay, let me do this. Handling both short and long responses simultaneously is also challenging, as they might exhibit very distinct preferences towards the bias variance trade-offs during bias variance trade-offs. What kind of trade-off is that? I don't know. During optimization. Last but not least, the sparsity of the reward signal from verifiers. The sparsity of the reward signal from verifiers is further exacerbated by the long chain of what? The sparsity. Because the longer because you get the reward only at the end at the result. So the longer chain of thought, then yeah, but you want to get result like the score for each token, not just the end result. But realistically, you can just check if the end result is correct or not, and not you cannot check if each token is correct. So you just have the reward for the end result. So the problem becomes even bigger because now you have long chain of thought, even more tokens, and none of them are getting scores or rewards. It's just the end result. So sparsity of the reward signal from verifiers is further exacerbated by the long chain of thought pattern. That's what I just said, which intrinsically requires better mechanisms to balance exploration and exploitation. To address the aforementioned challenges and fully unleash the potential of value model-based methods in reasoning tasks, we present value-augmented proximal policy optimization, VAPO, value-augmented, okay. The value model-based RL training framework. VAPO draws inspiration from prior research works such as VCPPO and DAPO, and further extends their concepts. We summarize our key contributions as follows. We introduce VAPO, the first value model-based reinforcement learning training framework to outperform value model-free methods on long chain of thought tasks significantly. VAPO not only demonstrates remarkable superiority in terms of performance, but also showcases enhanced training efficiency, streamlining the learning process and underscoring its potential as a new benchmark in the field. Streamlining the learning process and underscoring its potential as a new benchmark in the field. Sounds promising. I don't know. Let's see. We propose length adaptive. What is this? What is this GA guy? What is this? What is this? I need to Google this. What is in AI? Generalized advantage estimation. Yeah. You need to estimate the reward for each token, because you don't get the reward for each token. You just get the reward for the final output, final couple of tokens. So you need to estimate it for every token, I think. Yeah, that's maybe what they're doing. They are having this method that estimates rewards for every token. Okay. Okay. We propose length adaptive general. I forgot. So reward estimation, which adaptively adjusts the lambda parameter in Gaia general reward estimation uh, computation based on response lengths. By doing so, it effectively caters to the distinct bias variance trade-off requirements associated with response of highly variable lengths. I don't know what bias variance trade-off is. We'll see. As a result, it optimizes the accuracy and stability of the advantage estimation process, particularly in scenarios where the length of the data sequences varies wildly. I don't know what I read. Let's go 3. Uh, we systematically integrate techniques from prior work, such as clip higher and token level loss from DAPO, value pre-training and decoupled general reward estimation, whatever, from VCPPO, self-imitation learning from SEAL, and group sampling from GRPO. Okay, we got something from GRPO. So they integrate that as well. That's crazy. They integrate everything. Additionally, we further validate the necessity through ablation studies. VAPO is an effective reinforcement learning system that brings together these improvements. These enhancements work together smoothly, leading to a combined result that's better than the sum of individual parts. We conduct experiments using the Quen 2.532b pre-trained model, ensuring no supervised fine-tuning data is introduced in any of the experiments. To maintain, so this is just the pre-trained model, to maintain comparability with related works DAPO and R10 Quen 32b. The performance of VAPO improves from vanilla PPO a score of 5 to 60. What? So it goes from 5% correct answers to 60% correct answers. That's crazy if I understood it correctly. Surpassing the previous state-of-the-art value model-free methods DAPO by 10 points. So DAPO was the previous one. More importantly, VAPO is highly stable. We don't observe any crashes during training, and the results across multiple runs are consistently similar. Preliminaries. Okay, this section presents a fundamental concept and notation that serve as the basis for our proposed algorithm. We first explored the basic framework of representing language generation as a reinforcement learning task. Subsequently, we introduced PPO and generalized advantage estimation. I hope there won't be any maths, which there is maths, whatever. Modeling language generation as token level. What is MDP? Markov decision process, okay. Reinforcement learning centers around of policy that maximizes the cumulative reward for an agent. What is my head doing here? Okay. Maximizes cumulative reward for an agent as it interacts with an environment. In this study, we cast language generation tasks within the framework of the Markov decision process. If only I remember what this is, bro. Let's take a quick look. Google the images quickly. Agent, environment, reward, state. Okay, this is the classic reinforcement learning diagram. Agent, action, state, reward, whatever. Okay. Let the prompt be denoted as X and the response to the prompt as Y. Both X and Y can be decomposed into a sequence of tokens. Yeah. For example, prompt X can be expressed as X0 to M, where the tokens are drawn from a fixed discrete vocabulary A. Okay. We define the token level Markov decision process as a tuple. It's tough. We got some kind of SAPRD0 omega. Here is a detailed breakdown of each component. State space. This space encompasses all possible states formed by the token generated up to a given time step. What? At time step t, the state st is defined as... Okay, I understand. Okay, the state st is the input prompt, so sequence of tokens in the input prompt and sequence of tokens in the output prompt until the token t, and token t is at the time step t. So I guess state t plus 1 would be the same input prompt and output prompt until token t plus 1. So that all is the state at t plus 1. Okay. State space. Why it's called space by the, I don't know. Action space. It corresponds to the fixed discrete vocabulary from which tokens are selected during generation process. Okay. Okay. I'm streaming for like 2 hours now. Okay. Let's go. Dynamics. What is this? These represent a deterministic transition model between tokens. Given a state st, which is sequence of prompt tokens and sequence of generated tokens until timestamp t, and action a is equal to y t plus 1, okay? That's the action. The action is just the token that it generates. The subsequent state s t plus 1 is just the current state of s t and additional token y t plus 1. The probability p of s t plus 1 given state t and whatever a. What is a? What is a? This is the first time I see this a, bro. Okay, I don't know what a is. The probability of the next token given the current token, and I'm guessing everything before it, is 1. What? I don't know. We'll see this. We'll figure this out. Termination condition. The language generation process concludes when the terminal action omega, typically the end of sequence token, is executed. So here we see state action. So this is state action, the next token. P is probability of the next token given previous tokens, I guess. I don't know. Reward function. Wait, A is action. Yeah. Wait, yeah. Okay, I get it. Okay. We get a sequence of tokens and we get a certain action. And depending on the sequence of tokens and the action, this action will give us 100% this token that it chose. So this action already chose a token based on this sequence. So the probability 100% based on action and state, we can get the token 100%. So it's already chosen based on action and state. That's how I understand it. Okay, reward, given state and action. This function offers scalar feedback to evaluate the agent performance after taking action A and state S. In the context of reinforcement learning from human feedback, the reward function can be learned from human preferences or defined by a set of rules specific to the task. Chill out. Okay. We have one generation, second generation generated text in RLHF. I guess human preference is this one. And then reward is going to reward each token in this. Preferred, I guess. I don't know. Somehow reinforce the generation. I don't know. We'll see. But we know that this R here is now reward. And what is this D0? That's the only thing left. Initial state distribution. It is a probability distribution over prompts X. An initial state S0 consists of the tokens with what? Initial state S0 consists of the tokens within the prompt X, okay? Yeah, this is within the prompt X. So D0 is the probability distribution over prompts X. I still don't know which probability distribution, but I know that initial state is like the initial prompt. Yeah. I still don't know what D0 is, but it is what it is. Reinforcement learning from human feedback, learning objective. We formulate the optimization problem as KL divergence regularized reinforcement learning task. This just means the changes that this reinforcement learning algorithm can make are not too big. So if it tries to make too big change, then it will get clamped onto a smaller change, reduced. So yeah, the training is more stable and slower, not crazy, and it doesn't introduce mistakes. Our objective is to approximate the optimal KL regularized policy, which is given by, okay, stuff. I don't know. In this equation, age represents the total number of decision steps. S0 is a prompt sample from the dataset. RST80 is the token level reward obtained from the reward. Oh my God. Okay, let's go. I can't. PPO uses a clipped surrogate objective to update the policy. The key idea is to limit the change in the policy during each update step, preventing large policy updates that could lead to instability. That's the KL divergence thing, KL regularization. Let policy. You have some policy. So this policy is the LLM. So the policy has state, which is prompt, and gives action, which is which token is the next. B, the policy parameterized by, what is this? I forgot. Okay. So this is just the language model and has these parameters. And old policy, be the old policy from the previous iteration, from generating the previous token. The surrogate objective function of PPO is defined as, oh God, what is this? Oh God. Okay, where R of theta, theta, is the probability ratio, AT is the estimate advantage at time step T, and what is this? Is a hyperparameter that controls the clipping range. So we multiply the reward, probability ratio of the current token and the previous token. For some reason, I don't know why. And we get some estimated advantage, so estimated reward, because we are just getting reward for the last result, like in the chain of thought. So we don't know these rewards for the previous tokens, so we need to estimate them. We have another, I guess, neural networks that estimates the rewards, maybe. Okay, it is what it is. Generalized advantage estimation is a technique used to estimate the advantage function more accurately in PPO. It combines multiple step bootstrapping to reduce the variance of the advantage estimation. For a trajectory of length t, the advantage estimation at challenges in long chain of thought reinforcement learning for reasoning tasks. Long chain of thought tasks present unique challenges to the reinforcement learning training, especially for methods that employ a value model to reduce long chain of thought tasks present unique challenges to reinforcement learning training, especially the methods that employ a value model to reduce variance. Value model, yeah, this is this guy. General advantage estimation neural network, whatever. In this section, we systematically analyze the technical issues arising from sequence length dynamics, value function instability, and reward sparsity. Value model bias over long sequences. What stamina made? Battery low. Ah, yeah, battery low. Okay. Okay. You know, Evan, turn adorable. He's also making these long streams, and I can't lose. So need to make it a bit longer than him. Okay. Okay. Turned on battery. I hope my thing doesn't overheat. As identified in VCPPO, initializing the value model with a reward model introduces significant initialization bias. I don't know what I read. This positive bias arises from an objective mismatch between the two models. The reward model is trained to score on the end of sequence token, incentivizing it to assign lower scores to earlier. What? The reward model is trained to score on the end. Yeah, when it sees end of sequence token, it generates a score, a reward, incentivizing it to assign lower scores to earlier tokens due to their incomplete context. I don't understand. In contrast, the value model estimates the expected cumulative reward for all tokens preceding end of sequence under a given policy. Yeah, we have this separate model neural network that estimates reward while the model is generating, trying to guess how good the tokens are and what the reward will be in the end, or depending on like the result the tokens give. During early training phases, given the backward computation of Guy, there will be a positive bias at every time step t that accumulates along that. I don't know. I don't understand. Maybe we'll understand. Let's see. Another standard practice of using Guy with lambda 0.95 might exacerbate this issue. The reward signal are end of sequence. A determination token propagates backwards as to the teeth token. So we get some reward. It somehow propagates back to the token number t, and then this token number T would get this like part of the reward. I guess the reward is divided between tokens, but I see that there is some kind of bias that makes like some tokens get more reward, maybe later tokens get more reward. I don't know. For longer sequences where T minus T is a lot bigger, you guys doing great work. Please create a summary blog from these sessions. That way you will have a timestamp artifact on your study sessions, to a video on your dev workflow, how you set it up for rapid prototyping. I don't know. Okay, I don't know. We don't even like. I don't know yet how to. There is a lot for me to learn as well here. So I'm guessing like throughout the future we'll be making more videos. I don't know which and when to help everybody contribute. This discounting reduces the effective reward signal to near zero. Consequently, value updates become almost entirely bootstrapped, relying on highly biased estimates. Consequently, value updates become almost entirely bootstrapped, relying on highly biased estimates that undermine the value model's role as a reliable variance reduction baseline. So what I understand is this model is trying to guess the value for each token before the value is assigned at the end. But there are some problems with length and some bias. I don't know. Okay. Maybe because there is a lot of this. Let's see what this guy explained. Okay, the goal. Train LLMs to excel at tasks requiring long logical reasoning. Easy. The method, reinforcement. The paper uses reinforcement learning, where the model learns by trial and error. It generates a reason steps, a trajectory, or thought process, gets reward based on whether the final. I know this. Value model. Okay, we read this. Okay, I mean value pre-training. Let's see. Challenge value model bias. Problem: initializing the value model incorrectly or using standard techniques like Guy with a fixed decay factor produces bias, especially over long sequences where the final reward signal gets heavily discounted. The value model doesn't learn accurate estimations. Explain this bias and reward discounting. Where does it happen? On which tokens? Okay, that's going to be the first question. The second, let's continue. VAPO fixes value pre-training. Value pre-training from VCPPO. Train the value model before the main reinforcement learning training starts using simple reward estimates, Monte Carlo, until it's stable. This reduces initial bias. Decoupled Guy from VCPPO use different methods to calculate how good an action was. The advantage for updating the value model versus the policy model. Use different methods to calculate how good an action was. The advantage for updating the value model versus the policy model. Use unbiased estimates. Lambda is 1 for the value model and potentially biased but faster converging estimates adaptive lambda for policy. I don't know. I'll tell it explain this. Explain this better, give examples. Okay, let's see the third question. Okay, challenge 2, heterogeneous sequence lengths. Problem, reasoning chains can be short or very long. Okay, see you later now. Okay, see you later. Or very long. A fixed guide parameter lambda might be good for one length, but bad for another. Too much variance for short, too much bias for long. Let me check here. Okay. Okay. Okay, so length variance is a problem. Okay. Token level policy gradient loss. Ensure the errors in long sequences aren't down-weighted compared to errors in short sequences during updates. Ensure that errors in long sequences aren't down-weighted compared to errors in short sequences during updates. I don't know. Explain challenge 2 better and show examples. Challenge 3. Problem. For hard problems, the model might only get the answer right very rarely. Sparse reward. Getting a 1 or correct is infrequent compared to getting incorrect. The model needs to explore effectively to find correct paths, but also efficiently learn from the rare successes. Vapo's fixes. Clip higher from DAPO. Modify PPO's clipping mechanism to allow probabilities of potentially good low probability actions to increase more. What? Modify PPO's clipping mechanism to allow probabilities of potentially good low probability actions to increase more easy. Okay, I said PPO is clipping the change, so you don't want to make the change too big. But if the correct answer is rare, so the reward is rare, then you want to make the change bigger to the parameters, so it remembers, or this rare reward influences it, so it learns. Because it's very rare, it's not going to learn too much anyways. Encouraging exploration without destabilizing. Positive example, LM loss. Self-imitation. When the model does generate a correct reasoning chain, add an extra training signal to directly imitate that successful chain. Like supervised learning. This maximizes learning from rare success. I don't really get this, but what is this? What is this extra training? What is this extra training signal in positive example LM loss? Okay. Group sampling from GRPO. Instead of sampling one response for many different problems, are you streaming Twitch or Discord? I'm not streaming on Twitch, I guess. I'm not. Nor Discord. I don't have audience. I'm just streaming on YouTube and LinkedIn. I don't know. Maybe Twitch will work also. I don't know. Where was I? So group GRPO. Instead of sampling one response for many different problems, sample multiple responses for fewer problems in each batch. Yeah, that's from GRPO. This provides better contrastive signals comparing good versus bad attempts for the same problem. Key results. State of the art outperforms everybody else. We already know that. Very short training, reliability. Okay, we will just ask our 4 questions now. While it's responding. Okay. My LinkedIn stream is so weird, by the way. Okay. Oh my God. Let's see. It's answering question 4. Let's go. Value model bias and reward discounting. Why is my computer starting to go crazy again on the cooling? What is the value in this context? The value of a state ST, the sequence of tokens generated so far, like 2 plus 2 equals, is the expected total future reward. Expected total future reward. Okay. The model will get starting from the state, assuming it follows its current policy strategy. Yeah, it's expected reward. It's trying to guess how much reward it's gonna get. Why is my thing overheating? Okay, it's like asking, given I've written 2 plus 2 equals, how likely am I get a final answer right and get the reward averaged over all possible ways I might finish this calculation? Really? I thought it's like, it says like 2 plus 2 equals 4, how likely am I to get a good reward? Or 2 plus 2 equals 5, how likely am I? But it says here it's different. It says here, averaged over all possible ways I might finish this calculation. Why? Okay, this is tough. It's tough to understand. We'll understand it eventually. Don't worry. Bias, source 1. Initialization bias. The paper mentions initializing the value model using a reward model. These models have different jobs. A typical reward model used in reinforcement learning from human feedback is often trained to predict the quality, example, human preference score of the complete response. Yeah. It tends to give low scores to incomplete sequences, early tokens, let's go, and higher scores only when the sequence is nearly finished and looks good. Okay. Value model needs to predict the total future reward, even for an early token, like the first 2 in 2 plus 2 equals 4. The true value, if the model is perfect, should be high because it's on the path to the final correct answer and reward. Okay, so you can't really use reinforcement learning from human feedback reward model, type of reward model, because this is only going to give correct high scores if the generation is finished, because it's trained to do what humans like, and humans like finished generations and not like halfway generations. But this is not good because we need a model that's going to score tokens as they are getting generated. So in the beginning as well, we need to give like high scores to the tokens if they seem like they're going to lead to a correct answer. So bias. If you initialize value model using the reward model weights, the value model starts with the reward model's mindset. It incorrectly assigns low values to early intermediate tokens because they represent incomplete thoughts, even if those thoughts are essential steps toward the final reward. Okay. I swear, asking AI to explain to you makes it a lot easier to learn than trying to read the paper. I've just started to ask the AI to teach me as opposed to reading the paper. Thanks. I did not know LinkedIn had good streams. I used to be unnecessarily biased against LinkedIn. I will check it out as well. I might find fellow nerds. Actually, I got like so many research scientists from all of these papers. I don't know if from these exact papers, but Tsinghua University and Beijing University in China and Harvard and all of these. I got all of the connections. I'm just spamming them with connections, everybody. But you need to have like a good profile. Like I got my YouTube channel and some other like I don't know what I made. So when they get my like connection request, they can check like why who I am and what I do. So you need to show them that kind of stuff. Where which tokens? What is this? Where which tokens? This bias affects the initial predicted value VST for all intermediate tokens T before the final end of sequence token. It's most pronounced for earlier tokens. Okay, let's just ignore this sentence. I don't know what I read, but I know what before the ones before. Okay, am I long? This is so long. Bias source 2, Gaia discounting in long sequences. What is Gaia? General advantage estimation. I agree. Work in best way to show credibility. Work in public. Yeah, I heard about that work in public thing, but I don't remember what it is. Generalized advantage estimation is a standard way to estimate how much better taking action AT in state ST was compared to an average. Gaia is a standard way to estimate how much better taking action AT in state T was compared to the average action. So you know the average action, and for every possible action you calculate, is it better than average or worse than average, and how much. Okay, some formula. Gamma is the future reward discount factor. Future reward discount factor, yeah. Often one in LLMs, so we ignore it. Okay, so we ignore it in LLMs. Lambda is the Gaia parameter. It balances bias and I don't know what bias and variance are again. Like what is bias and variance? Reward discounting. Lambda to k terms means that the influence of errors rewards k steps into the future is exponentially reduced when calculating the advantage. Imagine a 100-step reasoning chain where only the final step t equals 100 gets a reward of 1. When calculating the advantage A0 for the every first token using lambda, the contribution to the final reward, when calculating the advantage A for every first token using lambda, the contribution of the final reward will be multiplied by the lambda, which is extremely small. Yeah, this is 0.95 to the power of 100. Okay, bias. I still don't know what's the advantage estimate A for early tokens becomes almost entirely dependent on the potentially biased value estimates. Let's skip this. I can't. I don't get it. Value pre-training and decoupled Gaia explained. Check my LinkedIn. Okay, it's all good. Okay. Get a better, less biased. Oh my God. Get a better, less biased starting point for the value model before the main PPO train. Okay. This is the value pre-training. Take the base model, Quen32B after supervised fine-tuning. Use PyRef. Okay. To generate many complete reasoning sequences, so use the, I guess, language model. Yeah. To generate many complete reasoning sequences, trajectories, for problems in your training dataset, don't update language model yet. For each generated sequence, calculate the final reward, 1 if the answer is correct and 0 otherwise. For every intermediate step t in a sequence, calculate the Monte Carlo return. Simply sum up all actual rewards received from step t until the end of the sequence. Wait, for every intermediate, so for every token in sequence, calculate the Monte Carlo return. Simply sum up all actual rewards received from step t until the end of the sequence. In tasks with only a final reward, what? In tasks with only a final reward, this is just the final 0 or 1 for all steps. Okay. So it assigns reward 1 if it's correct to every token. Now train only the value model to predict these Monte Carlo returns for each step. Use a standard regression loss like mean square. Okay. I think I understand it. We have a question prompt, generate bunch of different answers, then assign number 1, score 1 to each correct answer, and score 0 to every incorrect completion, every incorrect answer. And now, for all of the correct ones, we assign a reward of 1 to every token that's generated. So we want to reinforce those tokens that gave the correct answer by assigning reward 1 to every token. But I think it's not good to assign reward 1. So we're going to train another model that's going to assign different rewards, not just 1 to every token, but maybe depending on actually how good the token is. And since we will not wait for every time, like until the end, and then assign tokens after we see the result, we want to be able to assign tokens as the tokens are generated to assign rewards. So this new model will try to predict, like try to calculate the rewards. We will train it to calculate rewards based on tokens. It makes sense. It makes sense. So during training, it will see the entire, like it will know everything, but during inference, this new model, it will just look at the tokens and assign, try to guess rewards, how good the token is. Okay, why it works? Instead of initializing V with a reward model which has the wrong objective, yeah, because reward model is different. Like, okay, you're training V from scratch or a generic initialization to predict the actual summed future rewards experienced in the initial policy. This aligns the value model's initial objective with its true purpose in reinforcement learning, reducing the initialization bias. Okay. Basically, you want to train this model from scratch and not just initialize it with some like other model, because other reward model might be trained for something else. So you want to train it from scratch. Okay. Example, generate 2 plus 2 equals 5, end of sequence, reward 0. And 3 plus 1 equals 4, reward 1. Then, for 2 plus 2 equals 5, we will train our value model when the token is 2 to predict 0. Token is 2 plus. So we will just take each of the combinations and give 0 to each combination, because 2 plus 2 is not 5. So this is during the training. And here in the 3 plus 1, if we get 3 plus 1 equals 4, that's correct. So we will just take each sequence of tokens and assign 1, or teach the reward model to predict 1 as a reward. Do this over thousands of examples until V gets reasonably good at predicting the eventual outcome based on the current state. Yeah. Actually, kind of easy to do this, actually. Kind of easy. It's so simple. Just look at the final reward and then train the model to predict the final reward for each token. That's so easy. That's so easy. Decoupled guy. Use the best possible target estimate for updating the value model, while potentially using a different, more stable estimate for updating the policy model. Value model and policy model. When calculating the target of PPO updates, for updating the value model's goal is to accurately predict the true expected future return. The best unbiased estimate of this is the Monte Carlo return, sum of actual rewards. Oh my God. Okay, we got sequence A, B, C, end of sequence. Rewards 0, 0, 1. Current value estimate 0.3. Okay, guys, I'm too tired. I'm thinking like I should go and take a break. I can't concentrate anymore. 3 hours. Maybe I'll this. So if you want to continue reading, and maybe I'll just continue reading this in the next stream. Maybe, I don't know. Whatever I feel like doing, I guess. So I'm gonna tell you goodbye right now. See you maybe later today. End stream. Bye.